Good afternoon, everybody. I hope once again you can all hear me okay. If you can, if somebody could just, Gareth, maybe if you could let me know if the audio's okay. I took some mic technique advice from this morning, so hopefully that's improved things a little. Before we get started, I'll just do a quick introduction. I was very rude this morning, didn't introduce myself properly. My name's Gary Keenor. I work for Atkins and I'm a railway overhead line electrification engineer. So thank you all for coming on the live stream. For those of you on this morning, welcome back. What I'm going to do this afternoon is do a bit more of a technical talk and run through some of the basic ways that overhead line works, what it is, why it's important, how it works electrically and how it works mechanically. Before I do that, I just want to say a couple of things. Again, huge thanks to Lucy Pryor and Tracy Barber for setting up the Rail Human Library event, getting lots of love for it on social media today, lots of people getting involved. As soon as I'm done on here, I'm going to be jumping on to Being Charlie's live stream. I recommend you do the same. Gareth did one earlier, that was really good. So thank you to everybody, to all my colleagues as well who've really made the effort today under what are quite trying circumstances as well. As always, anything I say on this live stream are my views, not those of my employer. It's important that I say that. I think the way I'll run it, this is when I do this presentation internally, it runs for about an hour plus questions. So what I'll probably do is at the end of each slide, I'll have a look. If you've got a question, then I'll probably pick a question per slide. Obviously, if we get too many, it's going to slow it right down and we won't be able to get through to the end. So I will take questions as we go along. I apologise if your question doesn't get selected, but we do have a limited amount of time. So without further ado, and hopefully the technology will hold up. Okay, so I'm going to talk a little bit about some basic concepts of overhead line. Then we're going to have a little bit of a look at the electrical side of life, a bit on the kind of mechanical dynamics of it works, a bit on wiring, a bit on structures, and a bit on interfaces. And I'll try and keep it as generic as possible, but inevitably my experience is UK based, so there'll be quite a lot of examples from UK and Network Rail systems. So what is overhead line? Put simply, it's a system that delivers continuous electrical energy to a stationary or a moving train. There's lots, I'm not going to read all of these slides, you can read them for yourself, but there's lots of different ways of describing the system around the world. Everybody's got their own preference. I tend to use OLE because it's the UK norm, but it all means the same thing. Now, unique is an overused word, but the overhead line is genuinely a unique electrical transmission system because if you think about the electrical equipment in your house, for instance, or your flat, wherever you live, it's stationary. So that means that the load is not moving around. It behaves in a very predictable way. So that means that the electrical transmission system can be relatively straightforward. The problem on the railway is that our loads get up and start moving around the countryside at a couple of 100 miles an hour, different speeds, different directions, different positions on the circuit. So that makes it a far more challenging system to deliver because it's a twin system. It's power transmission, as with every other power transmission system, but it's also a sliding contact system. And it's that sliding contact that makes the system, a lot of the challenges in the system come from that sliding contact. It's also a very exposed system compared to maybe national grid transmission lines. It's far closer to the ground because it has to be, so it's more exposed. It's exposed to climate, it's exposed to wildlife, particularly birds. Birds give us a lot of problems. They get into air gaps and cause flashovers. It's susceptible to pollution and also to vandalism and trespass. Crucially, the contact wire, which is this thing you see here, this is the wire that's in contact with the train. The position of that wire is absolutely paramount. We must keep that wire over the top of the train on the operational range of the pantograph. If we don't, very bad things happen, as you'll see in a minute. And for that reason, it's a combined mechanical and electrical system, unlike transmission line systems, which are just basically electrical systems with some basic mechanical support. This is very much a mechanical and electrical hybrid system. I'm glad to hear the audio is working. Thank you for that, Gareth. No questions so far. Excellent. Okay, right. So why should we electrify the railway? Electrification is unusual on the railway. You can build a perfectly good railway without electrification, depending on your definition of perfectly good. You can't build a railway without track. You can't really build a railway without signalling. You can't build a railway without stations and bridges. You can build a railway without electrification. So, given all that, why would we electrify? It's not a cheap system to build, so why do we do it? Well, we do it for a number of reasons, and broadly now I'd split these into two groups: economic reasons and decarbonisation reasons. The economic reasons are simply that electric trains accelerate faster, which means you can get more trains onto your railway, which means more bums on seats, which means more revenue, more people using the railway. Secondly, electric trains are far simpler than diesel trains. They have far fewer moving parts, and therefore they have a lower maintenance cost, and they have higher reliability. Roger Ford has promised me, hello Roger if you're there, that reliability data would be great at some point. The data I do have suggests that electric trains are between 3 and 5 times more reliable than diesel. And that includes, by the way, dewires. Before anyone says it, that includes the occasional disruption that we have from overhead line. Because they're more reliable, you can have a smaller electric fleet than the equivalent diesel fleet, because fewer of your trains are out for service at any one time. So those are the economic reasons to do it. You also get lower track forces, so that means that Gareth's track renewals can happen a little less often, so that's good. Those are the economic reasons, but the reason it's really coming into play over the last 5 years, and it's really now a big focus, is decarbonisation. And let's be clear, overhead line electrification is the only viable solution for core routes, which see plenty of trains, for routes which go at reasonably high speeds, 80 miles an hour and above, and lots of trains. Conventional overhead line is the only solution, and it will be the only solution for the foreseeable future. We can also regenerate back into, when our trains are braking, they regenerate back into the national grid, so we can recover energy that way. So those are the reasons to electrify. Now, normally at this point I would show a video of the French achieving the world rail speed record in 2007, taking an electric train to the crazy speed of 357 miles an hour. I'm not going to do that here because it takes too long and maybe I'll get into some technical hurdles as well, but I will post a link. This video is on YouTube. I will post a link at the end so you can go and have a look for yourself. Now, I need to be honest here, not here to sort of make claims that I can't stand up. There are disadvantages to this system, and those disadvantages need to be addressed when you're developing a scheme, a project, or whatever. The key one, the one that everybody focuses on, understandably, is the high capital cost of installation. It is an expensive system to install, but you do get your money back over time. Remember, electric railways are cheaper to run. They're cheaper to run. So you will get your money back. Second big disadvantage is there's no redundancy in the system. So just to explain, for those of you maybe aren't familiar with terminology, redundancy simply means that you have a backup. So if our signalling power supply fails, we have a backup. If a system on the train fails, there's usually a backup. With the contact wire, it's not practical to provide a backup. You can't have a second OLE system that somehow swings into place. That wouldn't be practical to do. So what that means is you must get the design right. You must get the design right, you must get the construction right, and you must maintain it correctly. Otherwise, you have a vulnerable system. So let's just have a look at what we mean by a vulnerable system. This is a video. This has been on the internet, on YouTube, for many years. I'm not sharing anything that's sensitive or anything like that. This is just before we start the video. This is a piece of video taken on the roof of an inspection train, which is carrying an inspection pantograph and roof-mounted cameras. And it is running along, just checking the overhead line, and then unfortunately there appears to be a defect within the overhead line at one of the structures, and well, we'll let you see for yourself what happens. So it's running along about 70 kilometers, and it's hit something. And now the pantograph is damaged. Well, it's not so far. Things aren't looking too bad, but as you can see, we're still running along, and as soon as the pantograph rises above the contact wire, now that's the circuit breaker coming out, and now you're getting all sorts of fairly serious damage, which will need significant repairs. So to give you an idea, to get that overhead line back into play, probably looking at least 4 hours work on site, maybe more, to repair that. So fairly significant disruption, and that was only from relatively low speed. Okay, let's run through some basic principles, and then we'll talk about some electrical stuff. So we don't run, you might think that it's a single wire that runs all the way from one end of a route to the other, but it wouldn't be practical to do that, and I'll explain why a little later on. So for that reason, what we do is we split the overhead line up into sections of around about 1.5 kilometers long, and we call those tension lengths or wire runs. And at the end of each wire run, we will provide a tensioning device of some sort, but also, because we need to transfer the pantograph from one wire run to the next wire run, we have a transfer mechanism that we call an overlap. And I'll talk about midpoint anchors a little bit further on when we get into the detail of tensioning a bit more. Right, I'm going to stop for I can see a couple of questions here. So, do they regen into the grid? Yes. If you have a train with regenerative braking, we will regenerate on AC. If we're on an AC system, we will regenerate all the way back to the grid. On a DC system, it's not that straightforward because you've got rectifiers in the way. On a DC system, you typically regen so that other trains can use that recovered energy. Does current fragmented ownership of the railway make valuing electrification savings more difficult? That certainly was the case for a while. Thank you, Noel. That's a question from Noel Dolphin. I suspect a loaded question because Noel's got quite a lot of knowledge in this space. I think it probably makes it a little more difficult. I think it's better than it was. I think 10 years ago it was basically impossible. Train operators weren't terribly interested in electrification. But I think it's better than it was, and I think that the closer the Network Rail and the train operators get to government, the easier it's going to get. And this week's announcement, who knows, may improve that. Right, question for Simon. Gary, what is catenary? What actually is it? Right, okay. You're quite right to ask that question. There are two ways of looking at this. Let me switch to big view. Right. So this is a catenary wire. This is the upper of the two wires, and when you put this under tension and then hang things off of it, it forms a catenary curve. So some people would say that's the catenary, but other people would say that the whole system, these two wires plus the droppers, that's the catenary. Other people again would say it's the wires and the droppers and the things that hold them up and the masts and the foundations and the bonds and all the other stuff. I'll leave you to decide what actually is catenary. It's one of those misused pieces of jargon, I'm afraid. Good question, thank you. Would the section length change on high-speed lines? No, if anything it might get a little shorter. It might get a little shorter because I won't go into the reasons why. We'll get bogged down in the detail, but on high-speed lines you might be slightly shorter tension lengths. You might be limiting yourself to maybe 1200 meters tension length, but not significantly. Okay, right, let's carry on. Let me get my doofer. Let's see if we can keep this going. Let's keep some momentum up. Right, I'm going to talk a little bit. I'm not proposing to sit and read out all of these diagrams to you. You can have a look afterwards. I will put this video on YouTube and it will remain on Periscope as well, so you can have a look at it. But the key features of overhead line really are, if you work from the ground up, which I always like to, some kind of foundation, something to hold the structure steady in the ground or onto a man-made structure, some kind of mast, a support arrangement which will have insulation in it so that the earth part of the system, the mast and the foundation, is earthed and bonded to the rail, is separated from the live parts, which are the other side of the insulators. Then we have the upper of the two wires, the catenary. You can see the catenary, which is the one I spoke about here. And that supports the contact wire, this one, through a series of droppers. We will then also sometimes have what we call ancillary conductors. There's different kinds depending on the feeding that we're adopting. It could be a return conductor, it could be an aerial earth wire, it could be both. It could be an auto transformer feeder, but they will typically hang on to them directly onto the mast or on an insulator onto the mast. A lot of people misunderstand the purpose of the registration arm. The registration arm does not hold the overhead line up. It doesn't do that. It's free to swing. It can move up and down. It's there to provide lateral positioning so that position on the position on the pantograph is carefully controlled. So here's another view of a slightly different arrangement. So there's two things different going on about this. The first thing is it's a push-off cantilever rather than a pull-off cantilever, so it's pushing away from the mast rather than towards the mast. And secondly, rather than being a return conductor feeding system, it's an auto transformer feeding system. Right, one more question. What's my YouTube channel? That's a very good question. I will post my YouTube channel at the bottom of this Periscope when I've finished. Okay. Right, we're going to move into the electrical stuff now. A lot of people get a bit less sure about the electrical side of things, so I'm going to run through. It's going to be fairly high level, but I should mention, while I do remember to do this, if you want to know more about any of this, I will post a link to my book at the end. It's a free download. You can go online, download it, and there's a lot more in there than you're going to see on this talk. In terms of voltages, there are a variety of different voltages, but the world has effectively settled on sort of 2 or 3 key ones. In terms of mainline rail, 25 kV AC is the kind of worldwide standard now. So for new build, it tends to be 25 kV AC at whatever frequency your country uses. So in UK it's 50 Hertz, in Germany it's 16 2/3 Hertz. Whatever is the industrial frequency, that's what we use. However, you wouldn't want to use 25,000 volts on a tram system because you can't put that kind of voltage into a street scenario. It would be extremely dangerous. So for tram systems, the worldwide standard now is 750 volt DC, which is about the highest voltage that's really safe to have in a street environment. However, around Europe there is lots of legacy equipment, lots of legacy 1500 volt DC all around Europe. There's some 3 kV DC as well, and there's also quite a lot in Germany, quite a lot of 15 kV AC. Now that's the voltage that the train sees, but it is possible to transmit power at a higher voltage than the voltage that the train sees. So for instance, we on high-speed lines often use 50 kV to transmit power, but then the train still only sees 25 kV, and we use a clever feeding arrangement called auto transformer feeding to achieve that. Apologies, I will take the odd sip of water. I tend to find that my voice runs out otherwise when I do these things. In terms of currents, the current obviously depends on what the train needs to draw in order to move down the railway. But typical currents on a 25 kV railway, a mainline passenger train or freight train might draw up to 300 amps. So quite large currents compared to, for those of you not of an electrical bent, if you've got an electric cooker that's all electric and you switch everything on at once, you might draw 30 amps. So we're talking 10 cookers worth, if you want to think of it that way. But that's not really the current that people like me over at Line Engineers worry about. It's not the normal operation current, it's the fault current. It's the current you see when something goes wrong and current starts to flow into a short circuit. Under those circumstances, we'll typically see currents of up to 6,000 or even 12,000 amps. So that's a very significant amount of energy. 12,000 amps at 25,000 volts is 300 megawatts of power. So that's a lot of power. That's enough power to melt this 10mm copper bar that you see here. Melt it and potentially even start vaporizing it. So when we get those faults, we need those faults switched off as quickly as possible. Talk about that a bit more later. Okay, have a quick look, quick question break. What options are there for low resistance contact wire? So this is low resistance contact wire. This is I think this is copper silver. So this has got pretty low resistance. It's pretty high conductivity, this. The problem is there are materials that would have a lower resistance, but they are softer and they stretch. And since you need to put the system under mechanical tension and it needs to resist the wear of pantographs for around about 40 years, you don't want a soft material. So it's a balance. You can't just treat... What I said at the start, this is about a balance of electrical and mechanical requirements. That's a really good example. Thank you. That's a really good question. This might not be your knowledge. Are TOCs charged per kilowatt hour? What's the arrangement there? Okay, so if you go back 10 years, the arrangement was that train operators were not charged what they actually used. They were charged using a very complicated mathematical formula that didn't really bear any relation to the power they actually used. But that's changing. On-train metering is becoming a thing. It's now embedded within EU directives and is now being implemented, I believe, in the UK. I'm not an expert on exactly where we are with this. There may be other people in the chat who work for train operators who can help with that. I'm sure that I can think of at least one person who would know the right answer to that. But I know that on-train metering is coming if it's not here already. Does my book go into detail on regenerative braking? No, not really, but the next version's going to, because I need to write a section on how electric trains work for the next one. Right, if you'll just bear with me, my SLR has done that thing that it likes to do, which is to switch itself off once in a while. So do bear with me while I switch it back on. We're back in the room. That will happen about every 20 minutes. I apologise. This is a very jerry-rigged AV system. I do not have a webcam. Okay, right, let's carry on. Let's carry on with the slides. Right, going to do a little bit on feeding. Again, I'm not going to go into lots of detail on this. There's a lot more detail in the book than there is in this slide deck. One of the key challenges we face on the railway is that we supply our trains with single-phase AC. You may not be familiar with this, but your household supply is single-phase AC. But when you look at outside, look at pylons going down through the countryside, they are three-phase. You always see three wires, three of each wire. That's because it's three-phase. So we can't feed trains at three-phase. It's too complicated. So we feed the trains at single-phase, but we're feeding from a three-phase national grid. And if we just took all of our supply from two phases, the same two phases at every feeder station, we would unbalance the national grid so much so that that your domestic supply would start misbehaving, frequencies would wander off, motors in factories would start running backwards. It would not be good. And for that reason, the national grid imposes strict limits on the railway as to how much imbalance we're allowed to impose. So for that reason, what we do is at each feeder station down the railway, we take our supply from two different phases. So this diagram shows you the first feeder station we take from blue and yellow, second feeder station we take from red and yellow, and then third we take from red and blue, and we keep repeating that cycle. So that helps limit the imbalance. The problem with that approach is that you cannot connect those different circuits up. You must keep them segregated. And for that reason, we have to have a thing called a neutral section midway between those feeder stations. And a neutral section is a mechanical arrangement with insulators that we must have. And it causes us some challenges. They can be difficult to maintain, and they can be a known failure point. So it's just an example of where the electrical characteristics of the system drive the mechanical characteristics. And there's lots more examples of that I could give, but I'm not going to on this short talk. Again, I'm not going to go through this in detail, but what this is attempting to show is that each track has its own feed. So this is a 4-track railway that goes down to a 2-track railway. So each track has its own supply fed from circuit breakers. The crosses are circuit breakers. So each track has its own supply. And because each track has its own circuit breakers, we can take particular sections of this railway out for maintenance or in the case of disruption. So we can switch, we can take the circuit breaker at the end, each end of the section out, and then isolate that particular track and keep the others running. We can also move the feeding point up and down. So if, for instance, the feeder station on the right, if that transformer explodes or breaks down, then what we can do is we can reconfigure this supply. We can close the circuit breaker at the feeder station and feed through the feeder station from the left-hand feeder station. So it's an extremely reconfigurable supply, and that reconfiguration can be done in a matter of seconds in order to keep the railway running. Okay, no questions so far, so we'll carry on going. I'll talk a little bit about electrical clearances. So what do we mean by electrical clearances? Well, quite simply, a lot of our conductors have to be exposed. If you think about the electricity supply in your house, all of those cables are safely insulated. They've got a wire cover. You can't touch the conductor. It wouldn't be safe to do that. With overhead line, you can't do that. Because of the sliding contact mechanism, they have to be bare. So how do we insulate the live from the earth? Because you still have to do that to avoid short circuits. Well, the truth is what we do is we use a lot of air gaps. We maintain air gaps between the live equipment and between bridges, station canopies, signal gantries, and anything else that isn't live. So that means that we have air gaps, and we specify the size of those air gaps, and that's really, really important. So what you're seeing here on this little table is the current UK standards for air gaps. In an ideal world, we would have 600mm air gap, but that's often not possible, and achieving that could be very expensive. It would mean rebuilding a lot of overbridges, for instance, and that's not cost effective to do that. So we then got 2 extra levels, which is basic insulation and functional insulation, which we can use. Basic insulation we would use routinely. Functional we would use, but we would do some kind of risk assessment to make sure that that's safe in that location. This table's a little bit out of date now, and I need to update it because there are now further levels below functional insulation. We're now using clever things like surge diverters to reduce further the air gaps while still running a safe and reliable railway. And what that's allowing us to do is to retain more bridges and reduce costs in electrification, which is really important at the moment. We need to electrify. We need to decarbonise. So, yeah, so those are available as well. Right, couple of questions coming up before I go to the next slides. Sorry if you already mentioned it. I haven't. Don't be sorry. But how long can you go before we need to change phases? Depends how you're feeding. On a classic feeding system, our feeder stations are about 25 miles apart, roughly. It obviously varies depending on the characteristics of the route, how much train load you're drawing, but typically 25 miles apart. On an auto-transformer feeding system, the feeder stations can be much further apart. On my patch, which is in the west of England, between London and Cardiff, we have only 4 feeder stations, and they are roughly 80 kilometres apart. So auto-transformer feeding is 50 kV feeding. It allows you to have fewer feeder stations. Feeder stations are not cheap. They are anywhere from £10 million upwards. So the fewer of them you can have, the better. Another question from Peter. Hello, Peter. With modern systems, isolating transformers still required at stations? Now, I do not claim to be an LV, a low voltage bonding and integration specialist. I'm not. Generally, we don't have isolating transformers. Generally, we can provide segregation between the electrical systems without using them. And that's not to say we would never use them, but they're quite a sledgehammer to crack a walnut, really. There are other ways of achieving the segregation. We do use isolating transformers where we have AC and DC mixing, but that's a different scenario. So to carry on talking about air gap clearances, particular area where we spend a lot of time worrying about air gaps and maintaining those clearances is at bridges. Certainly in the UK, we have we suffer from being the inventor of the railway. We went first, and for that reason, we've got a lot of structures which were not designed with electrification in mind, with low bridge decks, low soffits, and very little room between the roof of the train and the bridge. So we'll spend a lot of time working out what the air gaps are going to be under a range of circumstances, and we have to include track tolerance. So the track maintainer will want to have some allowance for lifting the track over time. The OLE maintainer will want some tolerance for maintaining the overhead line. The overhead line moves up and down as trains go through, so we have to allow for that. A whole bunch of things we have to allow for, and it's quite a complex problem. And it's really a 3D problem. It's a problem that you need to look at three-dimensionally, particularly if your bridge has a complicated shape. So, part of my job and my colleagues' job is to spend a lot of time working out how to get overhead line through bridges. And on that, so Bryce, thank you, Bryce. Bryce is pointing out that there are now electrically insulated paint coatings being trialled. Yes, I'll just go. People hate it when I do this. Never go back a slide, right? Your audience always hates it, but I will on this occasion break my own rule. The picture you see there on the right is a surge diverter, and that's now being used in the UK in combination with insulating paint and an insulating cover to significantly reduce air gap clearances. And we've got clearances in the trial location as small as 50 millimeters, which is a real, so far the trial's looking really positive, and if that remains the case, then that could really unlock some cost savings for us. So yeah, thanks Bryce for reminding me about that, Bryce. Okay, let's talk about earthing and bonding. When you look at overhead line, you're really only looking at one half of the circuit. Those of you know electrical circuit theory, a circuit has to have two halves. You have to send the current out to the load, and then you have to bring it back again. The overhead line is the outgoing half of the circuit. The return half of the circuit is equally as important, and we design that return half, we call it earthing and bonding. We design it to provide a low impedance path, a low resistance path back to the feeder station, because that allows us to detect faults very quickly and switch that power off before that 12,000 amps starts to do damage. It is also there to keep everything that's earthed below a safe voltage. If you think next time you're stood at a station and you might lean on a lamp post or go and touch the side of the waiting room, obviously not under the current circumstances you won't be, but in normal times you will touch things on a station which are connected to the bonding system. So we don't want those exposed metal elements to rise in voltage, so the bonding system has to make sure those voltages are kept safe as well. And what we do basically on AC systems is we use the OLE foundations as an earth mat. We connect those foundations and the masts to the running rails. So we also use the track as part of the earth system, and we bond everything to that, and we tie everything to everything. We create a big mesh of a big mesh earth farm essentially. On DC, if we were doing a DC overhead line system, you do the opposite of that. I'm not going to get into DC in detail today because it's a whole subject in its own right. There's a horrible thing called DC stray currents, and you do not want DC stray currents getting out of the railway. So we will do the opposite. We will insulate the railway from everything else as far as we can. Right, got a question from Phil Daniels. How are signalling systems protected from high common mode current? Okay, I have a confession now. I do have a degree in electrical engineering, but to be honest, I've spent the last 20 years running away from the electrical side of life. Phil, I cannot answer that question. Thank you for finding the limits of my knowledge. I knew somebody would sooner or later. I don't know. Perhaps someone else on the chat can find out. If not, I will try and find out. I certainly do know some people. Some of the people I work with in Atkins would very easily be able to answer that question for you. So I'll try and find out for you as best I can do. Okay, so that's the electrical side. going to talk a bit about the mechanical side now, and talk about the pantograph, which is one of the most important components of the whole system. The pantograph is the device on the roof of the train which picks current up from the contact wire, delivers it to the train where it does useful work, and then gets returned back through the rails. Getting a pantograph to work at high speed is quite tricky. You've got a set of competing mechanical and electrical demands. Ideally, it would be extremely robust, except that actually that's the last thing you want, because if something does go wrong, you want the pantograph to break rather than the overhead line. Replacing the pantograph on a train would take a couple of hours in a depot. Replacing the overhead line on the East Coast Main Line or the Great Western Main Line would take multiple hours, would take you a whole day potentially, maybe even longer. So to a certain extent the pantograph is a sacrificial element, and that's out of necessity. So you're trying to make something that's robust enough to work but fragile enough to break when something goes wrong, and that's a really hard sweet spot to meet. Again, I'm not going to go through in too much detail how this all works. We have a head which has carbon strips on it, and those carbon strips act as the pickups. The carbon is the thing that runs along this contact wire. The contact wire is nice and hard. The carbon is relatively soft, and we replace those carbons at regular intervals, because again, it's much easier to access a pantograph in a depot than it is to replace overhead line. The pantograph has an upward force. There's a pneumatic piston on the roof of the train which pushes the whole system up and provides a nominally constant force, usually 70 to 90 newtons of upward force. So that's about 7 to 9 kilograms for those of you who aren't mechanical engineers. But we also have secondary suspension, usually on the head of the pantograph, and you'll see in some video later on how that all works. The aerodynamics of this is, at high speeds, the aerodynamics dominate actually, and the whole airflow over the roof of the train becomes the dominant factor. So you don't get a constant force. You're going to see that when we get to the video. It's not possible to provide a constant force. That would be the holy grail. The reality is you get a range of forces, and the job of people like myself is to keep those forces within acceptable limits. So let's just break down how this all works. Let's try and bring the two sides of the interface together. So this is a very simple little animation to try and illustrate that. So we have the train, we raise the pantograph pushes up on the wire gives, it moves upwards. We have the amount that it moves upwards is called uplift in response to the contact force. So the contact force pushes on the wire and the wire lifts in response. Now we're going to start, but once we start moving the train, once the train starts moving, that upward deflection of the wire starts creating a wave, and you get a displacement wave set up in the wire. And that wave will move in front of the train, but also will move back down the train. So it will propagate in both directions away from the pantograph, like so. And the key thing is that you never, ever, ever want your pantograph to catch up with the wave that it's created. If it does, you get loss of contact. You get the pantograph will bounce along the wire, and you get loss of contact, and that's not good. It's not good for the timetable. It's not good for this. You'll start getting electrical erosion and pitting and all sorts of other unpleasant consequences. So we want the wave to travel faster than the train, and since the speed of the wave in a wire is a function of its tension, the faster you want to go, the higher the tension you put in the wire. And we'll typically set the tension so that the wave speed is at least 40% faster than the fastest electric train. The faster you want to go, the more tension. The more tension in the system, the more mechanical loads you see. Your components start to see more mechanical load. Structures tend to get bigger, and so on and so forth. So again, the demands of the system determine what it's going to look like, literally in a lot of cases. Excellent. I can see Anchor's helping me out here, coming to the rescue. Thank you, Anchor. So this is about a high common mode current, sufficient separation, and not having signal cables run parallel to OLE. So I think this is an immunisation question, if I'm reading this right. Yes, we have special measures that are in the book. I'm not going to go through them here. It's a whole topic in itself. But yes, there are special measures that we have electrically to protect low voltage systems like signalling from inductive coupling and those nasty electromagnetic effects that overhead line would otherwise have. Okay, sorry, I'll just stop that a second. That was a very simplistic animation of the system. It's more complicated than that in reality. This next animation is not actually an animation, it's a simulation. So this is a physical model of the system inside a computer. This is from a system that we have in Atkins called DRSS that we're quite excited about at the moment, which allows us to model the Pantograph overhead line interface and predict the behaviour. And we used this last year to solve a fairly thorny problem on Great Western at Steventon. So what this shows is a model of the overhead line with a modelled pantograph running down it, and then the actual forces and uplifts being assessed and captured as we go along. So we can use this system to fairly accurately now, and over time we're getting more and more accurate the more and more data we put into it, to accurately model how this system actually works. So the third thing I'm going to show you about the interface, because it is so important, is a piece of actual video. So this is shot from a test train. We run, as part of commissioning new systems, we will run test trains. So this is footage taken from the roof of a test train showing a pantograph running along. And crucially, the traces at the bottom are quite important. The two traces I think it's really interesting to watch are the top trace, the dark red trace, which is the stagger, the lateral position of the wire. You'll see that going backwards and forwards. And the bottom trace, the dark blue trace, which is contact force. And the contact force, again, is crucial. You do not want the force to drop below zero, because that means you're losing contact. You also don't want it to rise too much. Because if it rises too much, you're starting to put a lot of forces into the system, and you're beginning to get into that risk zone where you might cause damage. So it's about that sweet spot typically between 0 newtons and 300 newtons. So let's run that video. So as we can see here, so we're going through a tunnel at the moment. I think this is Alderton Tunnel on the Great Western. So you can see the wire moving backwards and forwards across the pan head. That's deliberate, that's stagger. We deliberately set the system to do that so that it doesn't wear a notch in the carbon, so you get nice even wear across the head. You can also see the contact forces. You can see they're quite lively. It's not a static force at all, but we're keeping it between 0 and 300. And you can see that the secondary suspension, which is in the head of the pantograph, is absorbing all those high frequency small displacements, whereas the main arm of the pantograph is absorbing the lower frequency, larger displacements like you're seeing now. I think we're coming up to a bridge now, so you'll see the head begin to drop to get through the bridge. We will drop the wire to get through the bridge. There's an overlap. That was our two tension lengths coming together momentarily. So you can see the head rising, falling as we're coming down to a bridge now. Yeah, here comes the bridge. Dropping, dropping, dropping. There's the bridge, and then we begin to rise back up again. Okay. Quick question from Lewis Bergen. Was it the Frankentrain? I guess you're referring to the video. On this occasion, no, it wasn't. No, this is actually a Class 800 train that Great Western Railway kindly provided to Network Rail for using in the pre-energisation commissioning tests. Okay, so we talked about those contact forces and making sure that nothing bad happens to the pantograph, and these are some sort of illustrations of the sort of damage that can happen to pantographs. So what we're seeing here is pictures of the actual carbons. Although it doesn't look like carbon, that's what it is. And what we're seeing here is chipping. What we're seeing here is there's been some kind of defect somewhere in the overhead line which has just taken a little chip out of the carbon. Now it doesn't look like much, but that chip will then run all the way through the rest of the overhead line, and as you can imagine, as the chip runs, as it's doing this across the wire, getting shot there, then it's going to notch in and out of that. So it's going to, and if that chipping gets bad enough, it will start to damage the wire, and then the wire will damage the carbon, and you get into a vicious circle of damage. And then usually the first thing you know about it is when something fairly bad happens and you get a dewirement or some real damage. So that's what we're trying to avoid at all times. Okay, let's talk about how we actually suspend the overhead line. The key thing that you need to do is match the parameters of your overhead line to the actual use you're going to put it to. So if you're building a tram system, you're not going to use the same overhead line as if you're building high speed 2, for instance. At low speeds, a simple single wire system, just one of these, suspended in the air, just supported every 40 meters or so, is going to be absolutely fine. If you only want to go slow speed, that'll work fine. If you want to go a little bit faster, you need to start putting more elasticity into the system. So you'll then have a little bridle, which is the second one you see, and the third one. So the first 3 systems there are tram systems. You can go up to about 80 kilometers an hour with those systems. You don't need anything more complicated. It will be fine. Beyond 80 kph, you start needing to have a full second wire. And the reason for that is that the support points are very stiff, but midway between the support points is very elastic. And the faster you want to go, the more of a problem that is, because you'll start getting loss of contact again. So above 80 kph, we'll start having what we call simple catenary, which is a 2-wire system. If you want to go at really high speeds, 200 kph and above, you need to do a bit more than just have 2 wires. You need to have either pre-sag, or you need to have a stitch, or you need to have compound. I'm not going to go through how those work and what the benefits of each of them are. Have a look at the book, there's more detail in there. Another challenge that we have, a big challenge that we have, is that this stuff's great. Electrically it's great, mechanically it's great. From a thermal expansion and contraction point of view, it's not great. This stuff expands when it heats up and it contracts when it cools down, and a typical overhead line system might have to cope with a 50 degrees C operating range from a cold day to a hot day. So that means the whole system's expanding and contracting depending on time of day and time of year. So how do you deal with that? Well, the simplest way to deal with it is to just kind of stretch it, tie at each end, just like you would with your washing line at home, and then let it do its thing. And what that means is that on a hot day, the system's going to sag, and on a cold day, it's going to hog. Now, again, for slow speeds, that's okay. For tram systems, that's perfectly fine. It's not going to make a significant difference to the running characteristics. And for slow speed systems, we'll use that system, we'll just fix it at each end and let it do its thing, and that's called fixed termination. But if you want to go at higher speeds, that's not acceptable, because that sagging and hogging changes the dynamic performance of the system. So for mainline systems and for high-speed systems, we use what's called auto-tensioned equipment, which is where we put a tensioning device at each end of the wire run, and then we allow the whole system to expand and contract around one fixed point, which is in the middle of the wire run, which is called the midpoint anchor. And the way that you provide the tensioning, that could be a set of weights, it could be a spring, it could be a gas tensioner. In the UK, for a long time, we used weights. Now we're moving to springs because they have certain advantages over weights. So let's have a look at how that works. So just to explain this diagram, the top view, you're looking down on the wire run, and in the bottom view, you're looking side on at the wire run. We've got a tensioning device at each end. On the left, we've used weights, and on the right, we've used a spring. In between, we've got the cantilevers, which are free to pivot in the horizontal direction, and in the middle, we have our one fixed point, our midpoint anchor. At the moment, we're in the middle of the temperature range, so it's about maybe 20 degrees C in the UK. That's the middle of our temperature range. So now let's see what happens when the whole system heats up. The system heats up, the wire run expands, the weights go nearer the ground, the spring takes up that extra length and winds up, and the tension remains nominally constant. Right, let's go back. We're cooling down again now, and we go back to the neutral. Now when we cool even more below the neutral, in the UK this might be minus 18 degrees C, for instance, a really cold day. Now the system's contracted, the fixed point stays where it is, everything else is free to move, and the weight stack lets itself out, and the spring winds up and lets it out as well, and the tension remains constant. And then we're back to the neutral again. So there's an extra thing here. I'm not going to go into drag. Drag's quite a complex concept to get your head around. I'm not going to worry about it today. If you're really interested in drag, then it's in the book. So we'll skip over that. So these are some examples of the kind of anchoring arrangements that we use in the UK, and you'll see variations on these themes wherever you are in the world. Top left is the modern spring tensioners that we use. Those are known as, the moment the ones we use in the UK are from a company called Fistra. There are other ones available, but we use Fistra in the UK. Top right is the traditional balance weight stack. You'll still see lots and lots of those around the UK. Bottom left is a fixed anchor. If you've got a very short wire run, you can have tension. You can have a spring tension at one end and fix the other end. You don't need a midpoint if it's a short wire run, so we would just fix it straight to a structure. And bottom right are, I believe those are gas tensioners. We experimented with those a few years ago. They're not as good as springs because they don't provide a constant force. So let's have a look. Thank you very much, Simon. Very kind words indeed. Thank you. Right, I can see I'm already running over time, which is absolutely what I always do at this point. We'll try and speed up a little bit. Conductors. Broadly, we have three pretty broad types of conductors. We have the contact wire on the left. That's this one here. This is a special wire. It's not really a wire. It's a bar, and it's got this. I don't know whether you can. Yeah, no, I'm not going to be able to persuade my camera autofocus. My camera has excellent AF detective faces, but it will ignore anything else I wave at the camera. But you can see on the left there, it's got a grooved notch, and that notch allows you to clamp things to the wire, but without interfering with the running face. So that's the contact wire. For everything that isn't in contact with the pantograph, we will use a conventional stranded cable, like the one you see here, and the one in the middle. If it's not a conductor that's under tension, we use copper alloy because it's good under tension, but it is quite expensive compared to aluminium. So for cables like bonding cables which aren't under tension, we will use aluminium simply because it's cheaper. Excuse me, camera's doing that thing again. Just bear with me while I get back on. Getting quite good at this now. Right. Yeah, so ancillary conductors, we'll use aluminium wherever we can. We said at the start that it's paramount that we keep the wire within that operating range of the pantograph. We do not want the wire going near the ends of the pantograph. The ends of the pantograph is the danger zone. The end of the pantograph is where bad things happen because the pantograph's pushing up. If the wire slips around the end of that bit called the horn at the end of the pantograph and gets underneath, that's when we get into that dewirement situation we saw at the start. So we're constantly, and my colleagues and I spend, typically we'll spend our day working out the geometry of the pantograph in relation to the track, because the track is what we have to follow. The train follows the track, so we have to follow the track too. So we spend a lot of time looking at the geometry, not just, if you think about this contact wire, it only goes in a series of straight lines, and the track doesn't. And Gareth, if you're still on the call, if you could please work out a way of your track always going in straight lines, I'd be really grateful because it would make our job a lot easier. Until Gareth gets around to that, we'll have to keep worrying about this. But it's not just a static position, we have to worry about the blow off under wind. So this wire, under the action of a crosswind, will displace by a significant amount. Could be, 6, even 8 inches under real storm force conditions. So we have to calculate that and work out what we think the wind displacement will be and keep the wire on the pantograph even under those conditions. In terms of vertical geometry, the ideal overhead line system would have a single contact wire height that would not vary. And if you are working on high speed 2, for instance, or any other high speed line, that's exactly what we do. We will not vary the contact wire height. It is a fixed height. And if you have to rebuild a bridge, you have to rebuild a bridge. We don't have any level crossings on high speed lines. But on conventional routes, we don't have that luxury. We cannot deliver cost-effective electrification if we have to demolish every bridge. So what that means is that we go low through bridges, we reduce the contact wire height through bridges, but also over level crossings. For safety reasons, we have to go high over level crossings. So we will vary the height depending on where we are in relation to those features. And in between, we have a maximum rate of rise and fall that the pantograph can cope with. We can't start suddenly coming down at a 45-degree angle, for instance. It simply wouldn't work. So we have rates of rise and fall, which we have to respect, and that can be challenging when you've got bridges near level crossings. And again, those of you familiar with Steventon, the Steventon dilemma is not unique to Steventon. We have those situations around the network. So that's some of the things that as designers we spend a lot of time worrying about. Okay, talk a bit about structures. Overhead line structures have an obvious mechanical role to play. They have to hold the wire up and hold it keep it in its position. So we don't want too much deflection in the structure under wind or things like that. So it has to be relatively stiff. But it also has an electrical role to play. The structure is part of the earthing system. So the structure, that's why, for instance, we like galvanized steel, because it's an electrical conductor and it's a good conductor. And also the foundation is also a conductor. Even when we use concrete foundations, people sometimes aren't aware of this, but concrete is a good conductor of electricity, and we use the concrete foundations as part of our earth mat. That's for AC, I should say. For DC, we do not do any of that. For DC, we try, in fact, we will insulate the foundation from the mast to try and prevent DC stray current from entering the ground. Crucially, unlike maybe a civil engineer, if you're a civil engineer and you're used to designing a bridge, every bridge will have an element of being bespoke. Every bridge is slightly different. You cannot just, with the possible exception of footbridges, you cannot just pre-design a bridge and then plonk 10 of them along the railway. It doesn't work like that. For overhead line, it does. If you think about how many structures on Great Western, there are something like 10,000 OLE structures. You wouldn't want to design every one from first principles. It would take an age and it would cost a lot of money to do it that way. So what we do is we develop a kit of parts, a catalogue, a design range, which has pre-approved assemblies, pre-approved structures, and then we use that. And we use that system intelligently, and we roll it out along the railway. So in the book I go through in more detail. There are lots of different styles of structure you can use, but I'm just going to pick up on a couple of the most common ones. The most basic one is a single cantilever. You can see some examples of it here. There's different patterns, but they all broadly conform to the same thing. It's some kind of triangular frame holding one wire run over one track. They're great, they're cheap, they're easy to build, and they're easy to adjust when the track moves, or if you want to reconfigure, they're easy to do. And for a two-track railway, they're the standard. However, the railway isn't that simple. We don't always have two tracks. We don't always have two wire runs, one wire run per track either. So we need more complicated structures. And what we see here is what we call a portal structure. Again, this is used in multi-track areas. These are great because they're reconfigurable. Each wire run is independent of the other, so if one wire run breaks and you lose one track, the other three can keep operating. Obviously, some of you will be aware of headspans. Headspans do not have that feature, so that's one of the reasons why we tend to avoid headspans on main lines. Couple of comments. One from Lewis. My favourite overhead line height barge was the lowering of the track bed at Winchborough Tunnel. Yes, so what Lewis is referring there to is a track lowering. If you've got an existing structure and there isn't enough room to electrify it, our preference would be to rebuild the structure, but clearly if it's a tunnel, that's not appropriate. not possible to do that. So occasionally, if there's no other option, we will lower the track in a tunnel, but that is not a trivial thing to do. I think, from memory, I think Winchborough was shut for 6 weeks, or possibly 8 weeks while they do it. No doubt Lewis will maybe it may have the answer there, but to shut a mainline railway for 6 weeks is not something we would do lightly, but sometimes it is the only option in a tunnel. With bridges, we tend to try and avoid track lowerings unless we absolutely must. And as Gareth is saying, Gareth is a track engineer, is saying quite rightly, track lowering is bad, avoid at all costs. I'd agree, apart from the all costs part. But yes, track lowering makes drainage worse. It can undermine the foundations of the bridge. It's generally not a good thing to do. Okay, let's talk a bit about foundations. We use a wide variety of foundations to hold the structures up, and this is really where we draw on our geotechnical colleagues' experience. So I'm not a geotechnical engineer. Geotechnical engineering is a discipline and an art in itself. Understanding soil mechanics is difficult, and it's not always entirely possible to predict how soil mechanics will work at a given location. So we will. There's really two things we're trying to do with foundations. One is to match the soil mechanics, and the other is to have something that's quick to install. We do not want to be there for hours and hours and hours pouring concrete or trying to put something in the ground. So we use a wide variety of different things. So we've got, top left, we've got a concrete planted mast. We wouldn't install those these days because planting masts is time consuming. Top middle, we've got a concrete auger. We'll use those where the ground conditions are poor. Top right, we've got a gravity pad. We'll use those where ground conditions are extremely poor and we do not have good quality soil at depth. Bottom left is a steel driven pile with a bolted base. That's kind of the standard in the UK at the moment to use those. Bottom centre is a rock anchor. The little inset there is a pin base structure. I'm not going to go into that here, but it's in the book. But we'll also fix things to station roof work, to retaining walls, to bridges, to viaducts. We have to put an OLE structure every 50 metres, so whatever's there, we will have to find a way of fixing to it. Okay, basic design ranges, we've kind of touched on that already. A basic design range is a catalogue, is an OLE system designed to do a particular job. So in the UK we currently have 3 or 4 design ranges that we would use depending on the line speed, depending on how many pantographs the trains are going to be carrying. We would use the appropriate catalogue for that. And within the catalogue we have standard parts, standard components, standard arrangements, but also a set of rules that govern how you apply those arrangements. And sometimes we might find that there isn't the part that we need in the catalogue, in which case my company like Atkins could develop an additional part and then get that put into the range for everyone else to get that benefit from. Right, I think we're on the home stretch now. We're sort of on time, not doing too bad. This is my final couple of slides. Everything I've spoken up to now is about how the OLE system works, but actually making an OLE system work is actually the easy part of the job. The hard part of the job is making the OLE system work with all of the other railway systems. And it doesn't matter which railway discipline you work in, which railway discipline you talk to, they'll all say the same thing. The hard part is the interfaces. Getting everybody's kit to work with everybody else's kit is the hard part, because we've all got our own requirements and quite often they come into conflict. So good example, I've just said I'd like my OLE to go in a straight line. Gareth needs to go around curves. So there immediately is a constraint. Gareth wants to put his switches and crossings at a particular location, but I need to put a structure there and I can't get a structure in at that location. So over and over again we see these interface constraints and conflicts, and really for a design engineer on the railway, we'll spend probably most of our time actually dealing with those interfaces and working with our colleagues in track, civil, signalling, M&E, stations, environment, and all of this, working through all these issues and working out who's gonna compromise on this issue, where's that sweet spot between meeting everyone's requirements. So I'll just quickly rattle through what those interfaces are and then we will finish the session. The most important interface is the one with track. I'm really pleased, by the way, that the Permanent Way Institute now are offering a home for overhead line engineers. So if you are an overhead line engineer, I commend the Permanent Way Institute to you. Their view is that the track and the OLE is all part of the fixed infrastructure, and that's absolutely right. So we must follow the track. We must understand where the track is now, where it's going to be in a year's time, where it's going to be in 20 years' time. We must understand the alignment of the track, the curvature, what the cant is on the track, where the point work is, where those tracks diverge and converge, because our wire runs have to follow those divergences and convergences. The second really important interface is with the civil and structural element. So we've already talked about clearances to overbridges. We've got clearances to station canopies, to signal gantries. We've got foundations and fixings. We will quite often lean very heavily on our civil colleagues to develop fixings to parapets, fixings to station roof work. Anything that's a man-made object, we need the civil engineer to help us with that. And they will often also help design some of the foundations for us. It might not be obvious what the signalling interfaces are, but they are very significant, and we spend a lot of time worrying about them. We've obviously got all of, in terms of the actual signalling equipment, we've got all the electrical clearance issues that we have to all the other signalling, to all the other equipment, because the signalling equipment is earthed, and our equipment's live. But we've also got some additional interfaces which we take very seriously indeed. Undoubtedly, the most important one is signal sighting. Most railways around the world train drivers still drive using line of sight signalling. So that means that they're looking at the signal ahead of them, and they're reading the aspect, and they're obeying either a red signal, a yellow signal, or a green signal. It's really, really important that the overhead line does not obstruct that view of the signal. So whenever we do a new electrification or modify electrification, we will actually model that sighting. We will basically set up a virtual reality 3D model, and we will look at those drivers' line of sight views and make sure that they're not obstructed by anything that we've moved or put in the way. We also have immunisation. Signalling equipment uses electricity to detect the presence of trains and to communicate the right aspect to the signal head. And the electromagnetic interference that overhead line creates is very considerable. So we have to do a whole bunch of immunisation work within both the overhead line system, but also within the signalling system, to make sure that those two systems are compatible with each other. We have a number of interfaces with what we call electrical and mechanical services. You will also hear that described as E&P or possibly LV power supplies. This is station power supplies, points heating power supplies, basically any electrical supply that isn't the overhead line. So there's a bunch of interfaces there that we need to work with as well, so that we don't disrupt station supplies and things like that. And getting the earthing and bonding integration there is particularly important. And then beyond the sort of hard engineering disciplines, we also have a bunch of softer requirements and constraints and interfaces to deal with. We have to think about land take. Do we need any new land for this system? We need to think about ecology. Banging piles in the ground is disruptive to wildlife. We're not allowed to do things, for instance, certain times a year because it's the bird nesting period. We have sites of special scientific interest. We have areas of outstanding natural beauty. We have World Heritage sites. We have listed structures. And not least, we have the impact on our neighbours. Building electrification system can be quite noisy, involve vibration and dust and all those things, and we have to carefully manage when we're doing those activities so that we don't disturb our neighbours. So that's it in a nutshell. That's a very, very condensed. I do run longer versions of this for people who have a high boredom threshold. But thank you all for listening. I can see that we've got plenty of people listening in. In summary, overhead line is complex and it is unique. There is no other power transmission system like it in the world. In terms of feeding and sectioning, it's got a lot in common with other transmission line distribution systems. But once you get on the railway, this sliding contact begins to dominate the design and impose a lot of constraints on us. And we've got an awful lot of interfaces that we have to worry about in order to develop and deliver a railway that works together as a system. And in closing, the final thing I want to say before I go to any other questions is that if you want to know more about what I've spoken about, everything that I've talked about this afternoon and a lot more is in my free book. It is free. I'll say that again. It is free. You can download it from the internet. The web address is there, and I will link to it in the comments. So please do go download a copy of that. Everything I've discussed and a lot more is there. So in closing, thank you all for listening. Thank you for your questions. It's been really good, and I'll take a few questions. We've got a couple more questions now. Right, what have we got? Lewis has asked a question. Do you envisage wiring on the 4th rail bridge soon? Okay, that's a really good question. I'm going to be quite careful about how I answer it. So what do we know? We know that the 4th bridge is on a mainline trunk route. It is on an absolutely key route. It's on the route from Edinburgh to Aberdeen. We know that Transport Scotland and Network Rail in Scotland and the train operator in Scotland are all get that electrification is the only way to decarbonise. And actually Scotland are well on with they are on with a rolling programme. They've restarted their rolling programme. They're already developing some infill schemes. But beyond that, the next challenges are those trunk routes. So do I envisage it being done? Yes, I do. There are some challenges. There are some soft challenges. There are obviously heritage challenges. We need to come up with something that is sympathetic to the bridge. I think actually that's going to be a lot easier than on maybe, on some listed masonry structures. The nature of the 4th bridge absolutely lends itself to a sympathetic electrification. There are probably some clearance issues, probably some bonding issues that need to be worked through. But yes, I do think it will be electrified, and I hope to see it electrified in my lifetime. Absolutely. What have we got? Is there any feedback to signal driver in case of any faults? So yeah, it's a good question. If you're the driver of a train, you'll have a live line indicator in the cab. So it will be telling you whether or not the pantograph is seeing 25 kV. It'll also tell you whether the pantograph is raised. It'll also tell you whether the air circuit in the pantograph is acting normally. So it won't tell you if there's a defect, but it will tell you if something goes seriously wrong. You'll get a loss of line light indicator, and you may well get what's called an ADD, an auto drop indication. So the driver has some indications in the cab, yes. Okay, keep going with the questions. Lots of questions coming through. This is great. Will you be printing your book again soon? Yes, I will. We were intending to do that actually in the next couple of months, but obviously with the current difficulties we all have to deal with, printing and selling a book is way down my list of priorities, and I suspect way down everyone else's list as well. So at the moment, we're not going to do it right now, but as soon as we get some normality back, yes, we will be doing that. Excellent presentation. Still not convinced on regen to DNO grid. Well, I can assure you it does happen, and I'm quite happy to stand that up with some evidence if you need. When can we third rail everything from the CAM 1966? I'm not going to talk about third rail here. That's for another time. I think, yes. No, I'm not going to say anything more. Gareth, cheers Gary, have you and Being Charlie? Yes, so I want to wrap up these questions because I want to get on to Being Charlie's live stream as well. Noel said, to link back to the Human Rail Library, what are the challenges getting into electrification engineering? What the challenges getting into it? Well, we've come through a period where there's not been as much work recently, so the English programme stopped and we need to restart it. We need to restart it and we need to get a rolling programme back. And when we have a rolling programme back, the companies will begin to recruit again. And we need to recruit and we need to train the next generation. So the key challenge is to get to start with a slow but steady drip of schemes coming through. So we need some schemes on the table so that we can get that rolling program, so that companies like mine and others will see that the market is there, and will recruit for that market and train the people. Okay, thank you, Noel. That was a really good question. How can you make neutral sections shorter? They're already pretty short. You can't. The reality is you can't really make them short. I'm not going to go into the detail of that. William, yes, I thought it might be you, William. William looks at train planning, and William doesn't, quite understandably, doesn't like neutral sections because they impose limits on the headways on things like HS2. The way isn't to make them shorter. The way actually is to get rid of them altogether, and there are ways of doing that. There are ways of feeding an overhead line system without having neutral sections. Won't go through that here. Maybe for another time. We have a question from Bryce. Is tension monitored and linked to the control system so that power is cut if tension drops off? That's a really good question. Generally, no, it isn't. It isn't monitored, and the reason for that is that it's quite hard to monitor it, because your monitoring equipment would have to be intrinsically part of the wire run. So somehow you've got to put a monitoring system in place on a system that's up in the air. You could put it on the earthed. There is a short section of earthed wire run, so you could put it in there. But it's how do you do that and monitor tension? First of all, monitoring tension accurately can be quite difficult, and not then adding another failure mode. You don't want, whenever you're looking at a monitoring system, you need to have a monitoring system that doesn't add a failure mode. If you're monitoring something, but that monitoring equipment means that the overhead line breaks, then that you've done the opposite of what you intended to do. So it's a really good question, and I suspect there's probably somebody out there with a bright idea to come up with a system. I think that if you could make a robust system, it would have a lot of attention. The only other thing, of course, it would need a power supply, and that's a lot of power supplies potentially. So it would have to be solar. It would have to be completely self-contained. But yeah, it's a good idea. Good idea. Gareth says that's what the Silicon Valley tech bros should be inventing. Absolutely, a few less apps and a few more systems for maintaining, monitoring overhead line tension. Definitely. Right, well, it's 4:20. I really want to get off and see what Charlie's talking about on signalling, and you should do that too. Go over to @beingcharlie and go and see what Charlie's talking about. So I'm going to get off this call now. Thank you for listening. Thank you to everybody. Thank you to the organisers, Tracy Barber and Lucy Pryor. Thank you for the questions. It's been really good. I hope this has worked for you. Be good to do these more often in the future. And I will post, this will be on Periscope, but I'll also upload the video to YouTube. So thank you for listening, and goodbye.